So good morning, everyone, and welcome back to the third and last part of the Majorana Lectures. It's a really great pleasure to have the room full of people, of young people, also on the third day. By my experiences, this has not always been like that, so it's a good sign for our lecture series. The third part, please go ahead.
Thank you. So in the first lecture, I explained that entropy has two sides. There's thermodynamic entropy, but there's also microscopic entropy, which for, I think, originally Gibbs was the phase space integral of rho log rho, where rho was the probability distribution of a system in phase space, but for von Neumann, it has been the quantum, or since von Neumann, it's been the quantum analog minus the trace of rho log rho. And then I explained that Bekenstein and Hawking started with thermodynamic entropy, but entropy understood microscopically is important in more recent developments. But yesterday, we were essentially continuing with the macroscopic point of view, because I was explaining the Bekenstein-Hawking entropy from a path integral point of view, which is an old result that goes back to the 1970s of Gibbons and Hawking. Today we're going to discuss some more recent results that require looking at entropy more microscopically. And there actually are two that I'm going to explain. I'm going to explain Horacio Cassini on the so-called Bekenstein bound. And then I'll explain Aron Wall on the generalized second law. So roughly, I'll explain how Cassini proved the Bekenstein bound, except to prove the Bekenstein bound, he had also to explain what it meant, and then prove it. So he interpreted and proved the Bekenstein bound, and then we'll discuss how Aron Wall interpreted and proved a version of the generalized second law. So we learned yesterday that my estimation of how long things will take is unreliable, and that could also be true today. But in theory, what's going to happen is that we'll discuss the Bekenstein bound before the break and the generalized second law after the break. So what's the Bekenstein bound? Well, it goes back to, Bekenstein revisited his original idea about 8 years later. So remember, in his original paper, he'd considered a black hole absorbing radiation. And as long as the wavelength of the radiation was not bigger than the size of the black hole, he got a sensible result that agreed with the generalized second law. For long wavelength photons, it didn't work. In a later paper around 1980, Bekenstein considered some physical object. You could think of it as a table or a chair, a physical object. And let's say it has a size rho. And our black hole, let's say, has a size 2gm. Well, I'll tell you what Bekenstein said, and then there are lots of reasons it could be criticized. But Bekenstein said, let the infalling object have a size rho, energy E, and entropy S. So first of all, he assumes that if rho is less than r, the black hole can capture the object. Now that's the first point you could criticize. It's not obvious. I would think that a black hole could potentially capture a bigger object, maybe a little bit at a time. But anyway, since Bekenstein was ultimately vindicated by Cassini, let's just discuss what Bekenstein said and not criticize it too much. So he proposes that if the size of the object is less than r, then the black hole can absorb it. When that happens, the black hole entropy changes. The black hole entropy changes. It changes from, well, the change in the black hole entropy. Unless it's written in my notes, I'm not going to remember the factor of 16 pi or whatever it is. Okay, sorry. It is in my notes, so I'll try to get it right. Well, so the black hole entropy, which was area over 4g, in terms of the mass, is 4 pi g m squared. So the change in the black hole entropy is 4 pi g times m plus e squared minus m squared. But we assume that the infalling object is very light compared to the black hole. So that's approximately 8 pi g m e. So the change in the generalized entropy is approximately 8 pi g m e minus the entropy of the infalling object. But remember, 2 gm is the radius of the black hole. So we can call this 4 pi, or maybe let's use the diameter. 4 gm is the diameter of the black hole. And it's 2 pi times the diameter times the energy minus s of the infalling object. And Bekenstein wanted this to be non-negative for the generalized second law. So he said that this was the Bekenstein bound. Any object of size rho less than d and energy E, entropy S, is supposed to have 2 pi rho E minus S equal to or bigger than 0. Because that object supposedly could fall into a black hole of size rho. And the generalized second law, when an object falls into a black hole of size rho, would tell us this inequality. And what Bekenstein liked about this is that Newton's constant has disappeared. So he proposed that this was just a statement. I'm worried I've written it at the bottom of the blackboard. We can't see it. But anyway, he proposed this was just a statement about quantum field theory in the absence of gravity. So the Bekenstein bound was that, so rho, E, and S are the size, energy, and entropy of an object. And the Bekenstein bound was the claim that 2 pi rho E is equal to or bigger than S. And since Newton's constant nowhere appears, he proposed that this was a statement about quantum field theory without gravity. about ordinary physics, in other words. Well, if you're presented with a statement like this, one question, of course, is whether it's true, and the other question is whether it's interesting, assuming it's true. And so we have to ask two questions. Is it true, and is it interesting? When I ask, is it interesting, I mean, is it an interesting, non-trivial statement in the real world, or is it a trivial inequality? So no. Now, for decades, there was ample skepticism on both counts. So there was one argument that said that the Bekenstein bound was trivially untrue as a general statement about quantum field theory, at least. And the other argument appeared to show it was uninteresting. So first let's discuss why it appeared to be untrue. Well, untrue as a general statement about quantum field theory. Now, the people who argued that this was untrue as a general statement about quantum field theory allowed the possibility that it might be true in the real world. Maybe the real world, matter in the real world is described by some more special quantum field theory. But I'm about to give you an argument that ultimately is fallacious, as Cassini showed, but that for a long time made it seem that the Bekenstein bound could not be true as a general statement about quantum field theory. We consider a theory with n massive free fields. The spin doesn't matter, but to be concrete, you could call them scalar fields of the same mass m. Then you take a box of size d, and you put one particle in the box. So the energy is the mass of the box plus the mass of the particle. It's fixed, independent of n. And of course, the size of the box is also fixed. So the energy and the size are both fixed. And the entropy seems to be log n. Or at least it's equal to or bigger than log n. It's log n from choosing one of n particles to put in the box, and maybe a little bit more from the position of the particle or whatever. So this trivial argument seems to show that the Bekenstein bound is not possibly true as a general statement about quantum field theory. It would be violated for sufficiently large n. So maybe it's true in the real world, but it can't be a universal statement about quantum field theory. We'll see in a little bit that that's wrong. But anyway, that was the argument. Okay. Well, having decided it can't be true for arbitrary quantum field theories, let's just consider the real world and ask whether it could be an interesting statement about the real world. So let's try to violate the Bekenstein bound. So we could take a box of size d again. And we want to put in the box something that has a lot of entropy compared to its energy. Well, obviously, massless particles will be better than massive ones. And for a given amount of energy, the most you can do for the entropy is thermal equilibrium. So if you try to maximize the entropy at fixed energy, what does that is thermal equilibrium at some temperature T. So let's just put an ideal gas of temperature T in the box, then the entropy is of order dT cubed. The energy is actually of order d cubed T to the fourth. So what we call the Bekenstein ratio is Bekenstein says that S over E times D is less than 1 in order of magnitude. We could worry about the 2 pi. That's, okay, we can put it there. But. So that's dt cubed. Well, I'm dropping constants anyway when I write these formulas. So that Bekenstein says that this quantity 1 over dt is less than 1. But thermal equilibrium only makes sense. Thermal equilibrium in a box of size d only makes sense if T is much bigger than 1 over d. So the quantity that Bekenstein says has to be small, well, for this discussion to make sense, it's indeed small. But it doesn't seem like a very interesting constraint. Let's try to violate the Bekenstein bound. To violate the Bekenstein bound, if we want to try to violate the bound, well, this shows us that we will come closest to violating the bound if T is small. So we should take T of order 1 over D. That means the temperature isn't a useful concept. The closest we can come to violating the bound is just one or a few particles in the box. But now we should worry about the mass of the box. If the box only contains a few massless particles, the mass of the box is significant. And the mass of the box makes the bound uninteresting again because it'll make E much bigger than we're assuming. So we'd better get rid of the box. So the conclusion to make the Bekenstein bound interesting, we should look at one particle without a box. But the trouble we have now is that the notion of entropy doesn't make any sense if by entropy we mean thermodynamic entropy. To get to a regime where the Bekenstein bound was interesting, we had to go to a regime where thermodynamics doesn't make sense. So the Bekenstein bound isn't going to be interesting if we think S is thermodynamic entropy, which I believe is in fact what Bekenstein had in mind. So it's obvious that the entropy of a single particle without a box is a vague idea, but it's also true relativistically that the size of a single particle is a vague notion. So it appears that the terms in the it appears that Bekenstein's statement is ill-defined when it might be interesting. So that was also a view for a long time. Okay. Now I'm going to navigate toward explaining how Cassini explained what the Bekenstein bound means and how he proved it. But maybe I'll just stop here for a moment for any questions on this.
So questions? Other questions?
Okay, so we've argued that basically this bound is only interesting outside of really thermodynamical scenarios. I was wondering why the big N limit is an interesting scenario. I mean, how did we solve that issue related?
We haven't solved it.
Okay.
We will. Sorry.
Perfect.
You can ask the question at the end.
Okay.
So the large N scenario appeared to show that the Bekenstein bound can't be universal. But Cassini will, in a little while, explain that it is, with the right interpretation, it is true as a universal statement. So at that point, you can ask the question. Are there any more questions? Okay, well, we're going to need to know something about one fact from quantum information theory, which is called positivity of relative entropy. So there's a non-trivial fact that Cassini used, so I'm going to first explain that. So let rho and sigma be two density matrices for the same system. What's called the relative entropy between them is the trace of rho log rho minus the trace of rho log sigma. This quantity has an interesting interpretation, which we won't really have time to explain today, but I'll just briefly mention it. If your hypothesis is that sigma is the density matrix that describes a system, but you're wrong, and the correct answer is rho, you can ask how many copies of the system do you need to have access to so that you can learn by experiment that your original hypothesis is wrong. And the answer is roughly the inverse of this relative entropy. So the relative entropy determines how many copies you need to have experimentally before you can learn that a wrong hypothesis is wrong. The relative entropy between the true answer and the hypothesis determines how hard it is to disprove a wrong hypothesis. But for today, all we need to know is that S of rho and sigma is non-negative with equality if and only if rho equals sigma. So I want to prove that for you. And first, I'll prove it in the classical limit. The classical limit means that operators commute. So I'll assume that rho and sigma commute. So they can be simultaneously diagonalized. So sigma is the sum of what I could call sigma I, or I think I'll call it qi, times the projection operator onto state I. And rho is the sum of pi times the projection operator onto the state I. So you could think of sigma and rho as two probability distributions. In one state, the probability for the ith state is qi. In the other state, the probability of the ith state is pi. That's a description that would make perfect sense classically. And the relative entropy in that case also makes sense classically, of course. It's the sum of pi log pi minus the sum of pi log qi. And it has the same interpretation classically it does quantum mechanically. If you think the probability distribution is given by the q's, but it's really given by the p's. For example, you might have a coin that you assume is a fair coin. So you think if you flip it, it has a 50% chance to be heads. But maybe it's a biased coin, and the chance is really 51% to be heads. Well, first of all, you know that it will take of order 100 measurements to start to learn that the coin is biased. And if you calculate the relative entropy in that case, you'll find it's roughly 1 over 100. So that will illustrate the fact that the number of trials you need to disprove a wrong hypothesis is more or less the inverse of the relative entropy. Anyway, what we want to do is to prove that this is always non-negative. And I think all I will say about that is the following. If you minimize subject to the constraints sum of pi equals 1, which you can do by putting in a Lagrange multiplier. So you extremize this condition. You also want the constraint that the p's are non-negative. If you try to minimize it, you'll find that the minimum is at pi equals qi. A slightly better way to make the argument is to invoke some convexity. But anyway, by a little bit of calculus, you can show that in the classical case, the relative entropy is positive unless the two probability distributions are the same. So I want to explain the quantum case. So given rho and sigma, well, we can always diagonalize sigma. We then can't diagonalize rho simultaneously. But we can say the following. Let rho d be diagonal with the same diagonal matrix elements as rho. So throw away the off-diagonal part of rho and keep the diagonal matrix elements. So rho d is a density matrix because it's positive and has trace 1. So S of rho relative to sigma well, it's the trace of rho log rho minus the trace of rho log sigma. But you see, the trace of rho log rho is the same as the trace of rho d. The trace of rho log sigma is the same as the trace of log d, rho d log sigma. Well, let me write this out. I'm adding and subtracting the trace of rho d log rho d. Since sigma is diagonal, log sigma is also diagonal. And therefore, when I take the trace of rho log sigma, only the diagonal part of rho contributes. So I can just replace that with rho d log sigma. Then I've added and subtracted the trace of rho d log rho d. So I find that this is equal to S of rho d relative to sigma plus S of rho d minus S of rho. And we already know this one is non-negative. This we proved. Sigma and rho d are simultaneously diagonal, so we know that the relative entropy is positive. That was the classical calculation that I kind of sketched. So we're going to show that this other term is non-negative. The intuitive reason for it is that by taking a density matrix rho and throwing away its off-diagonal elements, we're making the state more mixed, which increases the entropy. But anyway, we'll give a proof of that in a second. So that will show that the relative entropy is the sum of two non-negative terms, so it's non-negative. And that fact is going to be the main input into Cassini's proof. Okay, so how do we prove that this is non-negative? We let rho t be t rho plus 1 minus t times rho d, where 0 is equal to less than t equal to less than 1. And the first thing is that the coefficients are positive. So rho t is always positive, and the trace is 1. So rho t is always a density matrix. Another fact is that rho t is linear in t, so rho t double dot is 0, which we'll use in a little bit. So now we're going to look at S of rho t, which is minus the trace of rho t log rho t. So S dot of rho t is minus the trace of rho t dot times log of rho t. You might ask why I don't have to differentiate the rho t inside the logarithm. If you do that, you'll eventually get the trace of rho t dot, which is 0, because the trace of rho t is 1 for all t. So S dot of rho t is this. And so one fact we're going to use is that S dot of rho t at t equals 0 is 0. So that's because S dot of rho t at t equals 0 is equal to, well, rho t dot, it's minus the trace of rho minus rho d times log rho d. Rho t at t equals 0 is just rho d, and rho t dot is rho minus rho d for any t. But this is diagonal, and this is purely off diagonal. Right? By definition, rho d was diagonal, and was the diagonal part of rho, so that rho minus rho d is purely off diagonal. So we have the trace of a diagonal matrix times a purely off diagonal one, so that's 0. The second fact, which we're going to show in a second, is that S double dot of rho t is negative. So together with the fact that the first derivative is 0, the second derivative being negative will tell us that S of rho 1 minus S of rho 0 is negative. But that's just S of rho minus S of rho d. Right? Because at time 0, rho t is the diagonal matrix rho d, just from this definition. If t is 0, rho reduces to rho d, and if t is 1, it reduces to rho. So having shown that the first derivative is 0 at time 0, if we can show this, we'll know that our corollary is that S of rho is less than S of rho d. So I think we need to use a convenient formula for the logarithm. So the logarithm of rho d is the integral from 0 to infinity ds, 1 over s plus 1 minus 1 over s plus rho d. Oh, sorry. It's rho t that we want. So that's true for numbers, so it's also true for matrices. Imagine diagonalizing the matrix And then for each eigenvalue, this relation holds. So S dot of rho t is equal to minus the integral from 0 to infinity ds of the trace of rho t dot times 1 over s plus 1 minus 1 over s plus rho t. So now we can just calculate s double dot of rho t. Well, remember, rho double dot itself is 0 because rho was linear in t. So I don't differentiate this one. I only differentiate this one. And so I get minus the integral from 0 to infinity ds, the trace of rho t dot 1 over s plus rho t dot 1 over s plus rho. Which is minus the integral from 0 to infinity ds of the trace of b of s squared, where b of s is 1 over the square root of s plus rho dot 1 over the square root of s plus rho. This is rho t everywhere. The only important thing is that b of s is a self-adjoint operator. So we have the trace of the square of a self-adjoint operator. So the trace is positive, the minus sign makes it negative. I may have lost you in that explanation, but what we succeeded in proving was that replacing a density matrix by its diagonal part always makes the entropy bigger. And that was the last step in proving that the relative entropy is always positive. Equality if and only if rho equals sigma. Okay. Well, now that we know about positivity of relative entropy, we're ready to discuss Cassini's proof. But maybe I'll just stop here for a second to ask if there are questions on this.
Question.
Can you give some comment on this very remarkable fact that in fact the entropy of the diagonal matrix is greater than the original density matrix, which is remarkable because we actually that's what happens when you measure, right? So you gain information, but by gaining information, actually the entropy increases, which is a purely quantum effect, right?
Yes, well, if you looked at the joint state of the measuring device and what is being measured, its entropy would not change. But the entropy of either one of them increases. They become correlated with each other, but if you forget the correlation by only looking at one, you have a more mixed state with more entropy. I think that's the best explanation I can give. Are there any other questions?
I think you can go on.
I don't see any, so I'll continue. So now we're going to discuss Cassini's proof. Well, I should say Cassini's definition and proof. So prior to Cassini, people didn't know what the Bekenstein bound was really supposed to mean. And the facts I told you at the beginning, where it was sort of appeared to be trivially wrong as a universal statement and uninteresting as a statement about the real world, made many of us, and certainly I was one, skeptical that there was a sensible definition of the Cassini bound, or of Bekenstein bound. But Cassini gave a sensible definition of the Bekenstein bound. So Cassini stated as a universal statement in quantum field theory. It's supposed to be true for any. This is quantum field theory in Minkowski space. So it's supposed to be true for any quantum state psi. So psi could be a state that contains a single particle. When we tried to see when the Bekenstein bound could be interesting, we ended up with something like a state of a single particle where thermodynamics isn't any good. But in Cassini's description, psi could be any state at all, such as a state of a single particle. And another state that quantum field theory in Minkowski space has is a vacuum state, which I call omega. And then Cassini considers the Rindler wedge. In Minkowski space. And we let rho be the density matrix of the state of interest for the Rindler wedge. And sigma instead is the density matrix of the vacuum. Sorry, I got it backwards. Sorry. Well, it's just notation, but if I reverse the notation, I'll get confused. So we let rho be the density matrix of any given state psi where we want to prove the Bekenstein bound for the Rindler wedge, and sigma is the density matrix for the vacuum. So we don't know what rho is, but yesterday we computed what sigma is. So sigma up to a normalization constant was e to the minus 2 pi kr, where kr is the integral from 0 to infinity dx of x times t00. 0. In other words, kr was the boost generator. We don't really know much about what rho is, but we won't have to. And then we use the fact that the relative entropy of rho relative to sigma is non-negative, since we just proved universal non-negativity of relative entropy in quantum field theory. In quantum theory. So what is that? Well, that's the trace of rho log rho minus the trace of rho log sigma. The sum is actually ultraviolet finite, but the two terms separately both have ultraviolet divergences. To avoid the ultraviolet divergences, Cassini added and subtracted something. So we'll write this as the trace of rho log rho minus the trace of sigma log sigma minus the trace of rho log sigma minus the trace of sigma log sigma. So I just added and subtracted a large constant. And the reason for doing that is that, as you'll see in a moment, these two terms are now separately finite. So what is the first term? The first term, well, minus the trace of sigma log sigma, is the entropy, the Rindler entropy of the vacuum. Minus the entropy of the Rindler entropy of the state psi. Now, remember, in the first lecture, I explained that Sorkin had the idea in around 1983 that Bekenstein-Hawking entropy was the entanglement entropy of a region. Here, the region is Rindler space. But Sorkin found that the entanglement entropy is ultraviolet divergent. But the divergence involves short distance fluctuations. And since any state looks like the vacuum at short distances, the entropy difference between two different states for the same region is actually finite, roughly speaking. Well, not quite universally, but very generically, it can be finite. I should say at the beginning, relative entropy is non-negative, but it can be infinite. So if we run into infinities here, it will be because the quantity we're actually interested in is infinite. Infinite relative entropy means that it's very easy to disprove your hypothesis. For example, if the coin always came up heads, after a very few trials, you would learn that your initial hypothesis was false. If you look at the definition of relative entropy, you'll see that it's infinite. The relative entropy between a coin that was always heads and a coin that is heads 50% of the time is infinite. And that infinity will be telling you that it's very easy. Only a few trials will start telling you that this is not a fair coin. So, but anyway, essentially this quantity is finite or potentially finite. And now let's look at the other quantity. So, okay. Well, rho is the density matrix of the pure state psi. So the trace of rho log sigma is equal to the expectation value in the state psi of the operator log sigma. And similarly, the trace of sigma log sigma is the expectation value in the vacuum of the operator log sigma. But luckily, we know what log sigma is. Log sigma is minus log c minus 2 pi times the integral from 0 to infinity dx of x times t00. Now, the constant c is actually divergence. But here, this thing, well, this thing that we have here is the difference between the expectation value in the state psi of log sigma and the expectation in the vacuum of log sigma. And since we're taking a difference, the divergent constant log c cancels out. Rather, as the entropy difference, taking the entropy difference canceled out the divergence Sorkin had found. So we have a difference of two terms. One of the first term we could call delta S. I'm sorry. Well, let me try to get the signs right. Okay. I better be more careful. So one is the entropy difference in Rindler space between the vacuum and psi. And the other, there's also another minus sign because of the minus 2 pi. So the other is going to be plus 2 pi times the expectation value in the state psi of the integral from 0 to infinity dx of x times t00 minus the same thing for the vacuum. So if I define delta S to be S psi minus S omega for Rindler space, Likewise, I want, let's see. Delta Kr, I could call it, to be this difference. The vacuum excitation value. So what we learned is that 2 pi delta Kr minus delta S is non-negative. So I explained that the vacuum subtraction was important to make the entropy finite, but the same is really true here. When you define the stress energy tensor in quantum field theory, it's really ultraviolet divergent. Usually we subtract a constant to make the vacuum energy density vanish. So with the usual definition, the second term is 0. But the subtraction made the difference well-defined, irrespective of how you define T mu nu. So we've proved that something is non-negative. But why is the something the Bekenstein bound? Well, Cassini's point, remember that when the Bekenstein bound was interesting, we didn't know what it meant. Because to make it interesting, we had a single particle without a box. We didn't know what was the energy, size, or entropy of a single particle. Now, we've interpreted the entropy of the single particle as the entropy difference for Rindler space between the state with the particle and the vacuum. And similarly, Cassini said you shouldn't define separately the energy and the size of a single particle. Cassini says that the substitute for E times D in the Cassini bound is the excitation value of Kr. That's the excitation value of the integral dx of x times t00. You see, if you have a system that's localized at some value of x of order d, then this will be approximately d times the energy. So if you have an object of size d, you can't localize it at a value of x less than d. So an order of magnitude for an object, if you have an object of size d and energy e, and you want to put it in the Rindler wedge, you can't make this integral much less than d times e. And we didn't know what the Bekenstein bound meant anyway. So Cassini told us that the correct statement of the Bekenstein bound is this one. Maybe we should call it the Bekenstein-Cassini bound. It has the virtue of being a well-defined and true statement, in contrast to previous versions of the Bekenstein bound. And in making this well-defined true statement, you replace the product of the energy times the size of the system with the excitation value of Kr, or more precisely, the difference between that excitation and the vacuum excitation of Kr. So that's the way the Bekenstein bound was eventually understood. Any questions on this?
Is it possible to generalize this statement to different regions, maybe with the appropriate symmetries, for example, the exterior of a black hole or, I don't know, the static patch of the sitter?
Well, you will find a few cases where you can generalize this. The crucial fact is that we needed to know what was the density matrix for Rindler space. So there only are a few classic cases where we know what are density matrices of some state. So for the static patch of de Sitter space, for example, we know what's the density matrix. So yes, the same argument would apply in that case.
Thanks.
Other questions?
Sorry, so the relative entropy is usually associated to the relative modular operator in algebra. So
To-
in this
To what? Sorry.
relative modular operator.
Yes.
So in this sense, the relative modular operator is a contribution blocked from entropy and energy, so like a free entropy.
Yes.
It's a free energy. in a sense.
Yes. Well, for brevity, I explained the relative entropy without introducing the modular operator. If we'd wanted to explain why relative entropy is better defined in quantum field theory than entropy is, I would have gone the route you suggest and explained the modular operator.
Other questions? So I have one, actually. Is this related to the Bousseau bound as well?
I don't think there's anything as simple to prove the Bousseau bound. I don't have an immediate suggestion to make. But after the break, we will discuss the generalized second law. That's getting closer to the Bousseau bound. Actually, yeah, okay. In my summary at the beginning, I forgot I wanted to say a little bit more on the page graph. Maybe we should do that after the break too? Or when are we supposed to take a break, would you say?
Well,
no. No? Okay. All right. So after the break, we'll try to keep some further remarks on the page curve short enough that we can discuss the generalized second law.
Okay, thanks. We reconvene at 11:50.
minus x times c0, 0 of the vacuum, you can actually make a state where the kr in the state is less than it is in the vacuum, and the left-hand side of the Cassini version of the Bekenstein bound is negative. The bound is nevertheless still true. The right-hand side is also negative. That will be a state in which the entanglement between the Rindler wedge and the other Rindler wedge is less than it is in the vacuum. See, the infinite entanglement of the vacuum comes because all possible modes in the Rindler wedge are entangled with their fellows on the other side. But in principle, you can manipulate any finite set of modes as you wish and reduce the entanglement in any finite set of modes. So you can indeed make states where delta S is negative, and you can make states where delta Kr is negative. Regardless of all that, the Cassini version of the Bekenstein bound is universal. Now, no one took me up on explaining what was wrong with the species bound. What was wrong with the disproof of the Bekenstein bound on the grounds that if you have very, very many particles of the same mass, and you put a single particle in the box, seemingly you have an entropy log n, which has nothing to do with the mass of the energy or size of the system. What was the fallacy in that argument? Well, the fallacy is that you're basically assuming that, that if you put one particle in the box, that's the only particle that's in the box. But you have to worry about particle-antiparticle pairs. And so there could be a fluctuation. Let's say I'll call it B bar here and B here, separated by a distance d with a mass m. What's the probability of that? Well, for a pair of mass m to be created separated by distance d by a quantum fluctuation has a probability of e to the minus m times d. But if there are n species, the probability is n times e to the minus md. So if n, I think I should call this e. We were calling it e in the lecture. Cassini's proof was universal, so it remains true in this region. Are there any more questions about the Bekenstein-Cassini bound? No questions? Well, when I summarized today's lecture at the beginning today, I forgot something, which is that I wanted to slightly improve on the discussion of the page curve. So when I discussed the page curve, I think it was in the first lecture, I assumed that the black hole started in a pure state. But I want to explain how you'd analyze the page curve if the black hole started in a low entropy state. I want to explain in what sense that doesn't make any difference. So we're going to do the following. We take what's called it will also be a useful introduction, sort of, to the generalized second law. We take a bipartite state AB, and we take any density matrix, rho AB. Now, you can always make a second density matrix. I'll call it sigma AB. Sigma AB is rho A tensor rho B. Rho A is the trace over B of rho AB. And rho B is the trace over A of rho AB. So sigma AB is a state in which individually the systems A and B have the same probabilities that they did in the state rho AB. But correlations between the A and B systems are ignored because the density matrix is a simple tensor product. So in the state sigma AB, if you measure only A or B, you'll get the same outcomes as in the state rho AB. But you'll find that measurements in A are uncorrelated with measurements in B. Now, we have then positivity of relative entropy. But if sigma AB is just rho A tensor rho B, then log of sigma AB is log rho A tensor 1 plus 1 tensor log rho B. So using that, this is the trace of rho AB log rho AB minus the trace of rho AB times log rho A tensor 1, or I could call it 1B, minus the trace of rho AB times 1 for system A tensor with log of rho B. But these three terms are all entropies. The first term is minus SAB by definition. But in the second term, since on B we only have the identity matrix, we can do the trace over B, replacing rho AB with rho A. And so the second term is the entropy of system A. Likewise, the third term is the entropy of system B. So our positivity of relative entropy has taught us that SAB, SA, let me write it, SA plus SB minus SAB is non-negative. That's called subadditivity of entropy. Now, there's one more fact which we need to know, is that there always can exist a system C such that the combined system ABC is pure. So if rho AB is the sum of PI times some states I of the AB system, and then you define a pure state of the ABC system, which is the sum of the square root of PI times I of AB tensored with I of system C, you'll find that for this pure state density, the corresponding density matrix of the AB system will be what I've written. So whenever you have a quantum system that's in a mixed state, you can always assume it's part of a whole universe that's in a pure state. And the mixedness came from its entanglement with some other system. And then, as I think I explained in the first lecture, it's true, if ABC is pure, then it's also true that SAB equals SC. Because the density matrix for system C has the same eigenvalues as for system AB, so in particular, they have the same entropies. So our inequality here could be written as the statement that SA plus SB minus SC is non-negative. But this is true whenever ABC is in a pure state. And ABC being pure is symmetrical in A, B, and C. So the same is true if I make a permutation of the three things. So it's therefore immediately also true that SC plus SB minus SA is non-negative. So I can combine these statements. The two statements combined say that SB is equal to or bigger than the absolute value of SA minus SC. That's called the Araki-Lieb inequality. Now let's apply it to the evaporation of a black hole that forms from a pure state. Sorry, from a mixed state, but a low entropy state. So a black hole in the real world doesn't form in a pure state, but it forms in a state whose entropy is very small compared to the Bekenstein-Hawking entropy. And then it evolves by unitary, well, it evolves by, we'll assume by unitary evolution. So after a long time, we have a mixed state of the black hole plus radiation. And the entropy, the combined entropy of the black hole and the radiation is small. It's equal to the entropy of the initial entropy of the black hole. So it's constant. Independent of time because of unitary quantum mechanical evolution and small by hypothesis. But S of the radiation grows. And our inequality says that S of the black hole at time t is equal to or bigger than the difference, absolute value and difference, between S of the radiation at time t and S of the black hole at time 0. So you see, now we're in almost the same situation as we were when we thought the black hole formed in a pure state. This is very small, and anyway is constant. The radiation entropy is increasing according to Hawking's calculation. The black hole mass is getting smaller, and we get a lower bound on the black hole entropy that eventually contradicts the thermodynamic entropy. In other words, we want the thermal entropy of the black hole to be equal to or bigger than the von Neumann entropy, the microscopic entropy of the black hole at time t. And these inequalities will eventually become contradictory at a page time, which is almost the same as it was before. The only difference from the previous discussion is that we've got this very little correction in the inequality. So when I presented it 2 days ago, this term was 0. Now it's something like 10 to the minus 20 for a black hole that forms from the collapse of a star. 10 to the minus 20 of the, compared to the large terms in the equation. So that's what I was going to say by way of improving the discussion of the page curve. Any questions on that? Yes?
Maybe a stupid question. What are the three systems, A, B, C here? I see two. You said the black hole and then you are considering the black in the inequality, the black hole at two different times in the inequality, one at T and one at T.
Sorry.
Yeah.
Sorry. Okay. The inequality, okay. Here's the black hole, here's the radiation. The inequality, as I stated it here, this version, well, C is the same as AB, right? I wrote it as that SB is bigger than SA minus SC, but SC equals SAB. So the Araki-Lieb inequality can be stated this way. And now, so what's playing the role of B is the black hole. What's playing the role? A is the radiation, and AB is the combined system of the radiation plus the black hole. If quantum mechanical unitary evolution is correct, then the entropy at any time of the radiation plus the black hole is the same as the entropy of the black hole at time 0, which is the way I wrote this formula. I probably skipped a step in writing it down. So the inequality we learned is that the von Neumann entropy of the black hole at time t is at least the radiation entropy at time t minus the black hole entropy at time 0. And now we have the problem. This is a very small constant. This grows linearly according to Hawking. And this one has an upper bound, which is actually getting smaller, the thermodynamic entropy of the black hole. So there's a page time where they meet, and this description has to break down. And it's almost the same time as it was before. On Monday, I assumed this term was 0. Today, I've just explained what's the version of the inequality without assuming that that's 0. Any other question? Well, during the break, I was asked a question that I found extremely embarrassing. In view of all these nice things I'm telling you, why do we feel we almost understand almost nothing about black hole thermodynamics? The reason we understand almost nothing is that the same as that we're stuck in the same way we've been stuck for half a century. If we take this picture we had yesterday of the Euclidean black hole as a semi-infinite cigar, for a path integral to be interpreted as a sum over quantum states, you should be doing a path integral in a circle, and the states propagated around the circle. And to an observer at infinity, that seems to be true. But the whole idea about the black hole is that it's not really true. The circle collapses to a point in the interior, and nothing is propagating anywhere. So we did a path integral interpretation, but it doesn't have a Hilbert space interpretation. The problem of black holes is that we don't know what we're talking about. We do formal calculations that don't mean anything. They give answers that seem to be consistent, which is what I've been lecturing about. But the fundamentals are completely absent that we would have when we do similar calculations in ordinary quantum mechanics or quantum field theory. So I clearly have failed to adequately explain that in these lectures. Now, if you want to keep me from now talking about the generalized second law, you have to ask a question on that. Well, so I'm going to discuss Aron Wall's proof of the generalized second law. And like Cassini's proof of the Bekenstein bound, it's partly a matter of defining what the statement is and partly a matter of proving it. So Bekenstein said that we should take A over 4G plus S out, and it should obey a second law of thermodynamics. But it was a little bit vague what was meant by S out. And so we're going to soon have more precise definitions. But we have to be very precise about what we're trying to prove. So okay. I'm drawing what's meant to be a Penrose diagram of a black hole. Well, I won't worry about what the picture looked like in the past. It was just Minkowski space maybe in the past. Up here is future in all infinity. Here's space like infinity at this corner. Up here is future infinity. And in general, as Hawking proved, classically, the black hole area increases. And Aron will only prove the generalized second law in a situation where we treat the quantum effects perturbatively. And if the classical area is increasing, then there's really nothing to say, because since the quantum effects are assumed to be of order h bar, if there's a classical increase in the area, that overwhelms whatever S out is doing. So we're going to assume that classically we have a stationary black hole. Stationary means time-independent horizon. It doesn't mean the black hole's always been there. Maybe it formed 1 million years ago and has long since settled down into a stationary state. But then there are quantum fields outside the black hole. So there's some quantum state psi if the quantum field's outside the black hole. And because of, we will interpret S out as a von Neumann entropy. And the von Neumann entropy of the quantum fields outside the black hole will be changing. And that will be part of the description. But the other part is that there will be a back reaction of the quantum fields on the area. And that's going to be small. Small means it's of order h bar. 1 over g is big. We might want to remember that there's really an h bar in the denominator. So the area dependence will be of order h bar, which will cancel the 1 over h bar in the denominator. So the area term will have a time dependence of order 1, and the S out also has a time dependence of order 1, since S out is inherently of order 1. And will prove that the sum of the two is non-decreasing. And in proving that, we will need to know how to calculate the area term. And just so I won't surprise you later, there isn't really going to be time to derive it today. But just so I won't surprise you later, I'll write down what the Einstein equations say about that. So I'll parameterize the horizon by what's called an affine parameter U. What that means is that the horizon is made out of outgoing null geodesics that never escape. They try to get out, but they just stay on the horizon. And the geodesic is always, there's a natural notion of an affine parameterization of a geodesic. So U is an affine parameter along these geodesics. And the Einstein-Raychaudhuri equation, well, people call it the Raychaudhuri equation, but it's simply a component of the Einstein equation. And Raychaudhuri actually originally did this time-like version. This is really Sachs's variant of the equation. But anyway, the Einstein equations say that d2a du squared is 8 pi g times TUU, a component of the stress tensor of matter, which we're going to interpret to mean 8 pi g times the excitation value in the state psi of TUU. Psi is the state in which we're going to try to prove that the generalized second law is true. So we need to know how the area evolves in that state. And it only evolves a little bit because of the quantum fields. And the Einstein-Raychaudhuri equation says that, it gives a formula for the U dependence of the area in terms of TUU. So at a certain point, we're going to need to use that. So then we're going to have to use another fact, which is called monotonicity of relative entropy. So I proved positivity of relative entropy before the break. We'd really need another lecture to prove monotonicity of relative entropy. One version of the statement is that if you have a system a bipartite system AB, and you have two density matrices, rho AB and sigma AB, the relative entropy of rho AB to sigma AB is equal to or bigger than the relative entropy between rho A and sigma A. I'm not going to prove it for you, but I will explain that if it's true that relative entropy measures how hard it is to disprove a hypothesis, then this inequality must hold. Because if you have the hypothesis sigma AB and you're trying to disprove it, you do experiments on the joint system AB. But one strategy you could have is to ignore system B and only measure system A. That's a special case of what you can do, so it can only make it harder to disprove the hypothesis. And the hardness of disproving the hypothesis by only measuring system A would be controlled by this one. But the hardness for a completely general strategy is this one. So if it's true that relative entropy measures the hardness of disproving a hypothesis, then this inequality must hold. Now, the version of that inequality that we'll use, though, is the following. We have a region of space-time U and a smaller region V. And we could look at when I speak of the relative entropy between two states, that'll be meant as an abbreviation for the relative entropy between the corresponding density matrices for a given region of space. Right? So if we have two states which are global states of the quantum fields throughout the whole universe, but we're also given a region of space where we're going to make our measurements, we would have corresponding density matrices. And I would then talk about the relative entropy. Maybe I should put U as a superscript on the density matrices. We'd have density matrices for the state psi and omega in the regions U. The version of the monotonicity of relative entropy we'll use is that the relative entropy gets less if you make the region smaller. If V is a smaller region, then the relative entropy between the two states in the smaller region is less. So relative entropy has to do with how hard, if you think the state is omega and it's really psi, and you try to disprove that by making measurements in the region U, it would be harder to disprove it if you make measurements in a smaller region V. So that's what this inequality is telling you. And there's something which I think is very nice. Monotonicity of relative entropy is a little bit hard to prove. But this particular case of it actually has a more direct proof, which I wish I had time to explain, but there isn't really time to explain it today. Now, Aron had the insight that generalized entropy can be interpreted as relative entropy. Well, okay. I'll have to tell you what the states are. Well, okay. Okay. So, relative entropy is always relative entropy between two states. One state, psi, will be the state of interest. The other state, omega, is something which I'll describe later. But Aron studied the relative entropy between the state of interest and some other state that we'll discuss, and used monotonicity of relative entropy to prove the generalized second law. So, I've told you one state. I'm promising to tell you a second state, but I also need to give you two regions. So in this picture, there's some time at the horizon at which you want to define the generalized entropy. Generalized second law means that the generalized entropy increases. So you take what's called a horizon cut. On the picture, it looks like the horizon cut is just a point, because the horizon is drawn as a line. But remember, angles are suppressed. So the horizon really is this line times a two-sphere. And the cut could be any cut. It could be a wobbly cut of the two-sphere. And then you connect this cut to infinity, space like infinity. And the space-time region you pick is the domain of dependence of that partial Cauchy hypersurface. So in this picture, it would be this whole rectangle. That would be region U. But then generalized entropy means that you're supposed to consider some other cut to the future of the first cut. Maybe the second cut is here. And again, you connect it to infinity. Oh, I should say about the region U, you should be able to see in the picture that the region U only depends on the cut, not on the particular space-like hypersurface I drew. I drew a space-like hypersurface just to explain the rationale of considering this region. The region is the domain of dependence of any space-like hypersurface that connects the given cut to infinity. Then we do it again with a later cut. And we construct a smaller region, which is V. So U is like this, like so, and V is like so. So then we have the fact that the inequality well, what Aron, okay. So now the generalized entropy is supposed to be defined for any cut. So what Aron did was to show that the generalized entropy is defined for any cut U, or it's supposed to be defined for any cut U. Bekenstein talked about it for any cut U. For any cut U, you'd have the horizon area at that time when you made that cut, and the entropy outside. So Bekenstein talked about it, and Aron defined it, if you like. And the generalized entropy at U, as explained by Wall, is a constant that we'll get to, minus the relative entropy between the state of interest in the region U and some other state I haven't told you about, also in the region U. But the constant term is independent of U. So the generalized entropy in region V is the same constant, again minus a relative entropy, but now in region V. Region V is smaller, which makes the relative entropy less, but because of the minus sign here, it makes the generalized entropy more. So it follows, well, once I explain to you what is the state omega, which will have the property that this is a sensible definition, it will then be true. It will follow then that the generalized entropy of V is bigger than the generalized entropy of U. For the relative entropy, the relative entropy in region V will be less than the relative entropy of region U. But the minus sign means that for the generalized entropy, it goes backwards. So just as Cassini reinterpreted the Bekenstein bound as a statement that a certain relative entropy is positive, Wall interpreted the generalized second law as a statement that a certain relative entropy is monotonic. It decreases when you make the region smaller. Yes? What? I think the question is, why does the constant cancel here? Well, it'll be clear why the constant cancels when I explain what the constant is. The constant will essentially be the area of the black hole in the far future. I think the next hurdle is to explain what is the state omega. So let's make the picture a little bit less busy. and just draw one region. So we had a cut U, we connected it to infinity, and there was a space-time region it produces. But instead of saying that the physics is determined by the data along this surface, I could equally well have picked this surface in the past. That's the pastmost surface that I could have used. And the futuremost surface I could have used is this one. So Aron picks this one. So we're going to think of the state psi as a state on the future cut. Sorry, the future, what shall I call it? Future surface. The future surface is this null surface at infinity and also part of the horizon. So from that point of view, the density matrix of the state psi for the region U is an operator on a tensor product of two Hilbert spaces. H of the horizon tensored with H of future null infinity. We want to think of these as being like HA and HB. So rho psi for region U is sort of rho psi for combined system, horizon, a bipartite system. One part is the horizon, the other part is the future. Now, I could trace over the horizon, and I would define rho psi just for the future. In other words, if I forget about what there is on the horizon and we just ask what an observer would measure at the far future in the state psi, there'd be some density matrix that would describe that. I'm supposed to give you another density matrix, sigma omega for region U. And we take it to be the same thing in the future. But on the horizon, we take it to be the density matrix of the vacuum on the horizon. So remember, at the beginning, I told you we're only going to worry about proving the generalized second law if the horizon is stationary. That means time independent. So being time independent, in quantum field theory in general, there's no notion of a vacuum in a given spacetime. But when things are time independent, then you can minimize the energy, and there's a well-defined notion of the vacuum, or ground state, the state of least energy. And the same is true on the horizon, given the hypothesis that it was time independent. We're assuming it's time independent because otherwise the generalized second law was trivial, because the classical Hawking area law was all we had to know. So we define a new density. It was a little oversimplified when I told you I was going to define a new state omega. I'm really only going to define a new density matrix. If you like, I'm defining a new mixed state, not a new pure state. So I define a mixed state for the region U, which is just the tensor product. On the horizon, we take the density matrix of the vacuum in the region U. By vacuum, I just mean the ground state of the quantum fields on the horizon. And on the future, I just take whatever is the state of the quantum fields in the state psi. So this is a density matrix. And it is true that the relative entropy between these two density matrices will be positive, but it will get smaller as U moves into the future. And the fact that it gets smaller as U moves into the future was Aron Wall's interpretation of the generalized second law. So if I let C be a parameter along the horizon, so that increasing C, you move upwards. Well, I could call it U, but C is for cut. U sounds like a single real number, but we have many finger time. We can move the horizon up different amounts in different places. So just imagine a general cut of the horizon. So well, so monotonicity of relative entropy says that if you increase C, the relative entropy for the cut at C between the states rho psi and the state I called sigma, that's the C derivative is negative, but that's d by dc of what? Well, of trace rho psi log rho psi minus the trace of rho psi log sigma. Well, that's d by dc. Well, this is minus S out, understood as the von Neumann entropy. In other words, by now we've learned that Bekenstein's S out, if we want to make any precise statement, has to be understood as the von Neumann entropy of the density matrix, which is exactly this up to a sign. So we have d by dc of minus S out minus something else is negative. But we can make the inequality go backwards if we change the signs. So we find that d by dc of S out plus something is positive. So all we need to do is to learn that this second term is the area on the cut C plus a constant. And if we learn that, then we will have turned the monotonicity of relative entropy into the generalized second law. So, since it was because I didn't want to whip something out of nowhere at the very end of the talk that I warned you at the beginning that we were going to have to use the Einstein-Majorana equation. Which tells us that d squared a du squared maybe is equal to 8 pi g times the expectation value in the state of TUU. And we're also going to use our handy result for log sigma c. You see, sigma c was supposed to be the density matrix of the ground state of the quantum fields along the horizon. And it really doesn't matter if it's the horizon of a black hole or a horizon in Rindler space. our discussion of the horizon in Rindler space can be carried over here. There isn't really time now to give a careful discussion of that. You will find it in Aron Wall's paper. Log sigma c is our friend, a constant minus 2 pi times the integral from c to infinity du. Well, so let c be defined by u equals u0. Then it would be here the integral from u0 to infinity du. I think I'm better off if I just call it u. I'll write this as u prime. What I've written is the Lorentz boost operator boosting the region to the future of a given cut. The cut is at some given value of u, the lower bound here. So I've been writing the formula like so. As an integral over a space-like surface. But a similar formula can be written as an integral over the future horizon. And that's what I've done here. I'm kind of taking some shortcuts in the explanation. A proper explanation, I should explain better exactly what's the state of the quantum fields on the horizon that does have this sigma c, this log sigma c. So I'm not quite going to do that, but I'll just say that if you'll imagine there's a formula like this, when I take the u derivative, I cancel the constant, that constant anyway, and I'm left with minus 2 pi times the integral from u to infinity to u prime of u prime minus u to u of u prime. The u derivative acts on this lower bound. Cancels this here. If I act on the lower limit, u prime minus u is 0 at the lower limit. And the Einstein-Regidori equation tells us that this is 2 pi times dA du. I know I'm breezing through this a little bit too rapidly if you haven't seen it before. But once we take... What makes the derivation possible is that we have this monotonicity of relative entropy, whatever the state sigma c is. And there is actually this handy state sigma c, which roughly is described by saying that at future infinity, the state is whatever it is in the state psi we're studying, and on the horizon, the quantum fields are in their ground state. If we take that to be sigma c, and then we also use the Einstein-Regidori equation, we find that this term in the inequality just involves the derivative of the area. So finally, the inequality does become well, we had S out. The Einstein-Regidori equation has an 8 pi g. Well, if I divide by 8 pi g, there's a 1 over 8 pi g. And then we get a 2 pi from the formula for log c. So we end up getting a over 4g. So I doubt you would be able, if you haven't seen this before, to completely understand it from my explanation. But I hope to have made it plausible that well, you have to use this rather tricky monotonicity of relative entropy. You also need a more careful discussion of why there's a state that has this density matrix. But given those facts, the monotonicity of relative entropy turns into the generalized second law. Yes?
Okay, it seems to me that this derivation is based on the fact that the horizon is shrinking, and therefore the future becomes more and more indistinguishable because the rest is the horizon. And it seems to me that does not depend at all on what is omega. It seems to me that you could put anything there, it will still be true. Or what am I missing?
It's very important that there is an omega. It's very important that there is a density matrix with the properties we assumed.
Right, but what omega is, where did you use that is the vacuum, for instance?
Well, for this derivation to make sense, there has to be a quantum field. There has to be a state of the quantum fields on the horizon, both the part we're studying and the part we're not studying, which has the property that the reduced density matrix in part of the horizon is that particular operator. If I picked a random operator, that statement would not be true. So the deep statement, which I probably didn't adequately explain, is that there is a state of the quantum fields on the horizon with the density matrix we assumed. So where I proved something like that was at the beginning yesterday, when we showed that the density matrix of Rindler space was this 2 pi kr. So it plus a constant, exponential of minus 2 pi kr times a constant. Well, you see, for example, if the constant had been anything other than 2 pi, there would have been no state of the quantum fields with that density matrix. Or if you replace kr by any other randomly chosen operator, there'd be no state with that density matrix. So the correlations, if you make a cut of the quantum fields, there are very subtle correlations of the quantum fields between inside and outside the horizon or across the cut. And if we make the wrong assumption, there won't be any state of the quantum fields with the density matrix we wanted. So the deep statement here, well, I would say the strategy is reasonably deep of Aron Moore's proof. So monotonicity of relative entropy is a very subtle statement. And the idea of interpreting the generalized second law as monotonicity of generalized entropy was a brilliant idea. And it's nice that the Einstein-Ricciardori equation is right. But the last thing that makes it work, which is quite subtle and which I haven't adequately explained, and you really would find a lot of detail in Aron's paper, is why I can assume that on the horizon there is some state of the quantum fields, which is given by the same formula that naively looks like what we had in Rindler space. That deserves a more detailed explanation than I've had time to give. Are there any other questions?
Could one turn around this argument and say the monotonicity of relative entropy gives you or derives the Einstein-Ricciardori equation?
Well, I won't dismiss that. In other words, could you, it depends on what you assume is known when you try to make such an argument. If you assume you know everything, almost except the Einstein-Ricciardori equation, then maybe you can deduce that one. Ted Jacobson has made claims a little bit like that. I'm not totally sure I find them too convincing, but some people like those arguments. Maybe I'm wrong. Any other questions? Yes? Just speak up.
Is there any reason that you don't find that interesting? Or that curiosity
Okay. Just continuing the same line of questioning inquiry, just want to know why you don't find it interesting. So,
Don't find what interesting?
this line of...
Oh, the story of deriving the Einstein equations from... deriving Ricciardori from... Well, I feel like it's something where you have to know the whole alphabet except one letter and you deduce the last letter. I don't find it... I don't understand the world in which you know everything except the Ricciardori equation. But I'm not sure that I'm right. Any other questions? I guess we'll call it a day.
So we thank Professor Witten for his inspiring series of lectures and all the attendants for the dedicated participation and for the time spent to give rise to this event. Thank you very much to all of you.